So good afternoon, everyone. I'm Jane Hilston, I'm Director of the LFCS, and it's my pleasure to welcome you all here to the 2013 Milner Lecture. Today, we have the great honor of having Eva Tardos with us to give the Milner Lecture. She perfectly matches the remit that Robin Milner gave us, that we should have a speaker who carried out good theory, but then took it into practice. And this is exemplified perfectly in Eva's work. So Eva Tardos is the Jacob Gould Schurman Professor of Computer Science at Cornell University. She received her BA and PhD degrees from Eötvös University in Budapest, and she joined the faculty in Cornell in 1989. Her work has been recognized a number of times. She's been elected to the National Academy of Engineering and the National Academy of Sciences and the American Academy of Arts and Sciences. She's an external member of the Hungarian Academy of Sciences and the recipient of a number of fellowships, including the Packard Fellowship, the Gödel Prize, Dancing Prize, the Fulkerson Prize, and the IEEE Technical Achievement Award. So you can see why we're particularly pleased to have her here today. Her work is perhaps most known for her work on network flow and algorithms, approximation algorithms, and quantifying the efficiency of selfish routing. But currently she focuses on algorithms and games on networks, in particular related to economics. And that's what she's going to be talking to us about today.
Thank you very much. So thank you very much for inviting me and for the great audience and interest. And what I want to try to tell you about is actually taking the work. If I want to go back thinking of what I did, and I guess Jane was nice to go back to the ancient history of what I used to do back many years ago. But if I only step back a couple of steps, then I've been thinking about quantifying or understanding the quality of solutions that we get on systems. This is a theme that unites what I'm doing with the games and what I did with approximation algorithms, where for whatever reason we're not reaching the optimal solution. This could either be because people are selfish or participants are selfish, or because we're computationally bounded. And we want to understand how well how much harm we're doing to the system because of whatever these issues are. I want to take this to a place in economics and auctions where classically, maybe the classical theories were trying to aim at finding the truly optimal solutions or the truly efficient solutions. And I want to try to take the theory of how we have thought about these systems that are not reaching the fully efficient or truly optimal solution in this other domain. So let me actually, instead of explaining every word in the title, what I'm planning to do is trying to talk about the words one at a time. So to start with, this sort of selfish behavior can hurt the outcome. That's exemplified by a classical story on the quality of the tragedy of the commons. The tragedy of commons is a cute story about some green pasture in which in a low village, everyone gets to graze some cows. And if you're a village resident, you can put your cows over there. And the story goes that it's in everyone's selfish interest to buy yet another cow. If there are enough people there, one extra cow will get you one extra thingy that generates milk, and that's good for you. Of course, then at some point there are too many cows on the pasture, and then all the cows gets corny, as the picture might suggest, and they don't give you enough milk, and everyone in the village really badly off, and they would have been better off if you only had one cow each. But instead of each having 3-4 cows, by then there's so many cows that they're all dying of starvation. So what we want to do here is set up a mathematical model that's trying to understand this kind of behavior. So the model would say, and I won't go very far with this model, but as an outline, is that the value for a single cow is a decreasing function of the number of cows that are on the pasture. The more cows there are, the less grass there is for a single cow. And with too many cows, there's no value left. You as a participant are only interested in the value for your cow or your cows. So putting an extra cow, a second cow on the pasture doubles your benefit, but increases the cows by 1. If there are enough people around, then the tragedy indeed occurs, and the selfish outcome is that there are way too many cows around, and the social welfare or everyone's happiness decreases compared to everyone restricting the happiness. This is a tale in which you're supposed to understand that natural selfish behavior in which everyone is trying to optimize their own outcome can easily have really dire consequences. The game theory can predict that if everyone behaves selfishly, then the damage we cause to society can be bigger than the advantage we do for ourselves, and that's exactly what's happening here. As a cow owner, my extra cow is a great benefit to me, and actually very little harm to all of you, except if we all do this, that very little harm adds up, and at the end we're doing a lot of harm. That's the story. I started to think about game theory in a context that's sort of more classical computer science is packet routing, where the model that so the two pictures suggest that packets can either be physical, like cars, or packets on the internet, where the model that we have been using is something that actually have been used in civil engineering in real traffic routing for much, much longer than computer scientists ever used it. And it's similar to what I had for the cows. We assumed that packet or traffic is subject to congestion delays, and again assume that the more packets travel on a switch or on a pass or on an edge, the slower it gets. To keep the model simple and natural mathematically, I assume it's a continuous monotone increasing function, more packets, more delays, and we also assume that the cost in the game is the delay. You as a driver, you as an owner of the packet, you're interested in getting your packets to you, from downloading a web page or something as fast as you can, or as a car driver, you want to get home as fast as you can. That's a natural selfish objective function, and what can go wrong again is that as I improve my delay, that is, I go on a path that's fastest for me, of course, on every edge I go on, I cause a little bit of harm to the rest of you by increasing the congestion, and as we've seen in the tragedy of the commons, that little bit of harm could actually be additive, and it could actually ruin the system for everyone. The main concept that's classically used in this area, and I'll come away from this in a second, is the stable or Nash equilibrium or stable traffic system. So a particular solution in which everyone chooses their strategy or chooses the path they drive on is at Nash equilibrium if, given what everyone else is doing, your current strategy is the best you know how to do. So for example, in the cow business and tragedy of the commons, putting a lot of cows on the grass is Nash equilibrium. True, if we all withdrew our cows, that would be even better if we all just had one cow. But given that you guys having 7 cows each, well, me too. 7 cows will give me a little bit of milk, at least 1 cow is practically no milk because you guys all have 7 cows each. So that's what Nash equilibrium is. Given that everyone's doing what they're currently doing, we all are doing our very best individually to optimize. And what's nice, and hence name out of Nash, Nash equilibrium exists, is always known to exist classically out of randomized strategies. I'm not going to talk about traffic routing, and I was learned over lunch of Kusha that those of you who are in his class will learn about this later. But I thought I should sort of tell you where I'm coming from. I said I originally thought about traffic routing as my main reason I got interested in game theory or selfish behavior, in part because I have been thinking about traffic routing or routing in graphs, as Jane summarized, before I ever thought about game theory. And I guess their main theorem is Tim Ravgarden, and by now more than 10 years old, was that in the traffic routing case, you can say something positive. And this is in a longer talk would be in contrast that selfish routing in traffic, just like the tragedy of the commons, is ample capable of ruining your experience. Okay, you are all optimizing the delay you individually having, but if life is unfortunate, then it could be really, really bad for everyone. If we all did the less selfish thing, it could have infinitely optimized everyone's experience. But there is something you can do, and one way we can express what we can do in a general way is that if selfish routing is not that horrible, it's no worse than having double traffic. Now, I don't know whether double traffic is something you're planning for, but I guess one way to read this theorem is that if the system is designed to tolerate twice as much traffic as what we're actually having, then the selfish experience is not so bad, or we actually express this with a more concrete version. In a capacitated version, if you model things with MM1 queuing delays, then I can make it more concretely. The selfish routing with capacity twice as much is cheaper than the optimal routing with half the capacity. So this says that, yes, there is a tragedy of the commons, and you also have an actionable move, namely you should up the capacity in your system, and that compensates to the damage that selfish behavior can do. So in some way, you should read this to say selfish behavior is not so bad. Okay, I'm going to stop talking about this, but this is sort of was my experience and where I was trying to come from, is to say that, you know, first of all, you can evaluate what the damage is to selfish experience, and in the tragedy of the commons, it was like really, really bad. It's not clear what we can do, and in this case, it seemed like we have a countermeasure. We should up the capacity and life gets better. And then more recently than this, I started to think about auctions on the web, and I want to spend the next 5 minutes convincing you that you should think about auctions on the web the same way we thought about traffic routing, and then I want to tell you what we can say about auctions on the web in the same vein as traffic routing. So what does selfishness do to you, and what can you say about this? So auctions on the web, or online markets, I'm thinking about a lot of different online markets on the world, maybe most dominantly advertising market. Advertising market, as I'll try to convince you in a second, it's actually a very interesting market. It's intellectually interesting to think about it. But among other things, this actually fuels the online economy. Like most of us, all of us, almost all of us refuse to pay for our online experience. Like any services that try to charge for your online participation are doing badly, and most of the internet, from Yahoo to Google to all of this, tends to be living off of advertisement profit because we somehow are not willing to subscribe. As a person or as a good dinner discussion, I'm happy to debate of what we can do as a society to convince people that this is a silly way to go. But basically, the industry converted into trying to live off of advertisement profit. And as I'll tell you in a second, it's a very interesting market to try to sell advertisement. So it's an interesting thing to think about. But it's not only advertisement. We have all kinds of effort markets. So Mechanical Turk, for example, or the other ones I listed there are all things where humans can take care of tasks and they get paid. That's also online markets. Or actually information markets, where you can buy all kinds of things. Or actually, if you check it, you get astonished how much these systems know about you, which is a scary perspective. And yes, they're selling it. That's what they're in. So there are all kinds of online markets. And in each of them, somehow, the system used to sell on these markets is very, very simple and elementary. In each of these markets, what's happening here is not a classical auction design. So let's just go with advertisement market. There isn't the case that when I go sit in my computer and decide to look up how to buy a ticket to fly to Edinburgh, then some fancy system sets up an optimization system to decide what would be the optimal ad to show me while I'm searching for my ticket for Edinburgh. But rather, within milliseconds after I open my browser, an ad will show up. There is a very, very fast decision system in which somehow decides which ad to show me as I'm searching for my ticket for Edinburgh. And what's better, this is a sort of repeated act, because not only I search for a ticket for Edinburgh, but then other people might fly to Edinburgh too, and they search for tickets. I want us to show them advertisements also. And these advertisements also competing for finding a solution. Now, classically, economic systems often get analyzed by using Nash Equilibrium as the outcome. That is, they think of this is a game, we should think of what our equilibrium strategies. This is not a very good match of what's happening in the online world. There is a complexity version of the not good match, which might be many of you heard about. A recent and celebrated result about Nash equilibria that they're computationally hard to find. So if something is computationally hard to find, 40 milliseconds is not going to be enough to find it. That's one problem. But there is also, there is something wrong about sort of learning what the game is. This is a repeated experiment in which I look for a ticket for Edinburgh, and then someone else looks, and someone else looks. It's not really a one-shot game. The one-shot game theory is a much better analysis when the, say, British government decides to open up some spectrum and they're running a spectrum auction. When that kind of thing happens, then there's usually years of preparation before it happens. So, you know, the government decides to do this. They usually set a date that in, 2017, they're going to run a spectrum auction. Then they spend a year getting advice from economists of what should be the rules under which they're selling the spectrum. They announce that. Then they wait another year where the bidders will try to figure out how they're planning to bid in this auction. And they spend a year trying to figure out what is strategically the right thing to do. And then they run the auction once. This is very different. First of all, you had 40 milliseconds to run to set up everything. OK, setting up happened ahead of time, but for you to bid, not a year, not 2 years, 40 milliseconds. And second of all, it's repeated. It's not exactly identical because I came here now and I don't know when I'm coming again. The next person for Edinburgh ticket is probably not me, but there might be many similar people to me. So it's in a sense a repeated experience and not a single shot experience, and we don't have enough setup time to figure out what the optimal behavior is. So what I would like to do, and I'll come back to this in a second, is take a solution concept that, or not only a Nash equilibrium, but something a lot more robust. So let's actually start by telling you what classically would happen. So again, if you want to think about ads, you can think about ads, or maybe you should think about spectrums, or you should think about that apple. This is a very simplest auction, which maybe all of you have seen. And the auction situation here is that we're trying to sell off that apple. And the classical answer to how to sell the apple is to ask everyone to tell us what the apple is worth to them. And here I have a slide which says how many US dollars the apple is worth to these people. I know the prices are not right in any currency. And the classical answer is that you're supposed to sell the apple to the person who has the highest value, because this maximizes value to the society. But then the classical solution also tells you that you shouldn't actually make him pay the number he said, because on that way he will never tell you what the value is. You should make him say what's called the second price. The second price is the second highest price, and the reason to do that is that it induces the people to tell their real value. Like he wants to win it, he wants to outbid the second guy, so it's good to say a number bigger than 5. If you made him charge the price, then he would try to say 5 and a penny, 5 and 2 pennies, or try to guess what the second price is, but this is very simple. And usually the simple mathematical model, as I promised everything is turning into mathematics here, is that the net value that this person gained is his intrinsic value minus the price. So he had a value of 7 for the apple, he paid 5, so his net value is here 7 minus 2 is 5. So this is the classically designed auction. This is beautiful and has every property you might want. Is truthful, that is, induces people to tell you they choose value. It's efficient, which means that we awarded the apple to the guy who valued it most. And it's incredibly simple. And in fact, a lot of the auctions online are sort of mimicking this in the simplicity of what they're doing. They're running some version of second price for hoping to get most of these properties. But usually they don't do a perfect job of mimicking it. And I guess here's some examples. Advertisement depends on what kind of advertisement, either sold on a first or second price. First price would be that you actually have to pay your price. You name the price and you pay it. That's usually how, for example, houses are sold, or repair contracts are sold that way. The contractor names a price and you either pay it or not. There's no second price business in here. But some ads are sold that way. They're usually sold on negotiations. That's effectively first price. Or second price, or something called generalized second price, which effectively is somewhere in between. The effort markets use all kinds of things. Some effort markets use what we call all pay. All pay means that everyone pays. The winner gets something, the rest of them do not. You might think this is a funny market, but effort's often sold that way. Effort is what? Effort is that you invest some energy. And while in a contract, we pre-agree on the contract, and then you repair my house, and the other people didn't have to repair my house. Online, it's a competition. You guys all submit something, and a winner will get $100. When you guys all submit something as an entry to the competition, you all did the work of entering the competition. The winner got something. So for example, the design of the current coin in India were sold on such a market. I don't actually know what the winner won, but there was a competition, everyone designed something, and someone turned out to have designed the actual coin in India, and that guy got a big reward, and the rest of them just did effort. That's all pay. Another version, it's sort of all pay, which is usually called the war of attrition, is we're running a competition, and then the last person in wins. So we all are exerting effort, except at some point we drop out. When there's only one person in, and everyone ups the effort because they want to win. I do more and more, and at the end it's just, say, Kusha and me, and then I drop out, and then he doesn't have to put in more effort. So that means we all put in some amount of effort, except for the winner who could drop out when I dropped out. He won. He doesn't have to up his efforts anymore. That also is an opaque kind of thing. These are all different kind of markets. Going back to this list of properties, they probably all satisfy this. They're pretty simple, and they fail both of those. They do all kinds of interesting things. It's definitely not truthful. It's not second price. That's pretty unique in truthfulness. And, competition, outcome of competition depends on all kinds of things, exactly, for example, how aggressively I bid. It may or may not come out that the winner is always the one that has the highest value. And so what I'm going to be interested in is trying to think of these auctions. So classical selling things or classical mechanism design was, instead of thinking about this, or maybe in addition, was saying, these things are flawed. They're not truthful, they're not efficient. Let's design another one. And what I'm going to do is just accept it. This is what we're doing. This is how things get sold. I want to analyze them. I want to understand the way I understood how much efficiency loss there is in routing because we selfishly route our cars or selfishly route our internet packets. I want to similarly understand how much efficiency loss there is in these systems because we use these and not the more complicated other things. So if I want to take truthful and simple to a comparative test, if there is actually nice truthful mechanism, Vickery-Clark-Groves mechanism is efficient. It assigns, the outcome is going to the person who can, or the groups of people who can best take advantage of it, but it's complicated to run. And there's actually another issue with the online systems. It's complicated to distribute the money. In the previous system, it was very clear who pays whom and how much. In the Vickery-Clark-Groves mechanism, there has to be a central organizer that collects all the money, and then it's unclear what he should do with that money. So there are some issues here. Whereas this is how things get sold. It's simple. It's not efficient and not efficient and not truthful, but that's how things work, so we better understand how good it is when we run things that way. Okay, so that's what I'm planning to do. I'm planning to tell you at the end of the talk, I think mostly, but sort of emphasize in the beginning, that there's a second big advantage of running things this way. And the second big advantage is that there isn't actually one market here. There are many markets. And if you think about spectrum auctions, you usually assume that the spectrum buyers are on a single market. Spectrum's only available, in my example, I said 2017. And you think about it, and you plan your business around it, And you're not thinking that if I didn't buy Spectrum on the Spectrum market in 2017, then don't worry, in 2018 there will be another one. The whole point there is there's a one-shot opportunity. In the kind of market I think about, whether it's effort market or advertisement market, the product's available in multiple places. You can advertise on eBay, or you can advertise on Amazon, or you can advertise on Google. You can buy effort on Topcoder or on Mechanical Turk. These are all options. If something didn't work out well for you on one, you can go to the other one. Or you can try simultaneously multiple things, which people are doing. Truthfulness, or this efficient and truthful solution, even as simple as second price auction, is a bit overrated in this sense. It works very well in the isolated markets, but when they're not isolated, there are issues, and I'll come back to this in a second. And in particular, these markets are all tied together. Their participants participate in all of them. And what's nice in the kind of analysis I'm going to offer in a second is that it works well with multiple markets. That is, if each of them are individual efficient, then the composed market will turn out to be individual efficient. So I promised you an example of what's wrong with second price. So let's just think about second price. And for making the example painful, you're buying a house. You live here and you would like to own your little house. And there are two houses on the market, the blue house and the yellow house. And unlike what's really happening in real life, we decided to go second price because we heard that was truthful. So here you are, this little boy here would like to buy the house. I don't know how to sell these houses, but second price. Remember, that's truthful. Not really, because the houses have current owners. So for example, if they sell them simultaneously, then you kind of can bid on one and not the other. You lost the bid on one, and the other house is gone. That's a pity. So it wasn't quite truthful. You should be a little careful here. You can't bid on both because you really don't want both houses. And if you did bid on both, you're in even bigger trouble if you win them both. So that's not very good. It's equally not good if it goes sequentially, one house after the other. It's similarly problematic. You say the blue house goes first. My value for the blue house is, I don't know what the right prices in this neighborhood are, but $500,000. Yeah, but you secretly believe that that second house, which is also worth $500,000, other people don't know how good that house is, so that will go cheap. You should not put in your real bid. You're really not interested in the first house for your real value because you know that there is a second house. And the second house has secret properties that other people don't know. That will go cheap. So you believe on what happens on the second house's market should affect of what you do in the first price. All I'm trying to convince you that it's not truthful. You should not admit your true value on the first house, because you know or think or believe that the second house will be available very cheap. So really, you'd rather pay less, right? So that's not truthful either. So when there are multiple markets, and what happened here, there were two owners, two separate owners of two separate markets. So similarly, whether you're on eBay and you want to buy whatever on eBay and you think that if you lose this one, this kind of product comes on eBay very regularly, there will be another one tomorrow. Or whether it's an effort market, you want to take care of something, and if the Topcoder people didn't want to do it, then maybe Mechanical Turk will take care of it tomorrow. There are always options that are very similar. It's very, very different from a unique opportunity such as the Spectrum auction, which is a classical one, or many other unique opportunities. This is not unique. So our goal is, and this is based on a paper, Vasilis Sirkanis, with a student of mine who actually is graduating, in case that's interesting to anyone, he's a great guy, that we want to design systems that are simple and have the property that when you prove efficiency in isolation, a simple isolated analysis, it extends to complicated markets that consist of this kind of individual markets put together. Okay, that's the main goal. So how do we do this? How do markets really work in real life, in economics, or in, when you go out shopping, how does life really work? Sorry, that was the goal. I should have switched earlier. How does this really work? The way life really works, so again, again, the paper is a bit more general. For today, I want to limit myself to something a little bit more simple. I'm going to run auctions for these food items, or if you prefer, for advertisement. And all I'm mixing is different kinds of individual item actions. The paper is more general, but this is maybe easier to think about. So you should think about that this guy, this whatever, fix, thank you. That fixing is sold on second price. This is sold on OPay. This is sold, OPay you can run on an Apple too. You guys all give me money, however much you want. Probably you don't want to give me more than a penny because you all have to pay. And the guy who gives me the biggest amount of money will get the Apple. That's called OPay. This guy is sold on second price and so on. I'm mixing different price and auctions. I'll tell you in the middle that what we're doing applies to much more general things, but it's simple to think of the plethora of single item auctions as an option for what I'm doing. Each person is interested in more than one item. They might be interested in more items. I generally will assume a decreasing marginal utility. Once you ate one fruit, you're less interested in the second fruit, or at least definitely not more interested, maybe equally interested, but not like your appetite for the next food is at least a monotone, non-decreasing function of how much you already ate, is the assumption here. And the key ID, which I'm taking from the supermarket, or from economics, is prices. Prices help. Auctions that have the property that they price the goods are the good auctions, because prices is something we all understand pretty well as individuals, or as individual selfish behavior. Prices doing a really good job of governing selfish behavior. When you have prices, you can optimally choose from prices, and turns out prices are very, very helpful. So let me start with the very simplest auction, which is going to have a unique property, and this is not either the well-known auction or the simplest auction, but the one that has this property. I'm going to run a single item first price auction. So first price is you name the price and you pay it. Okay, so here is first price auction. I ran for these cameras here, and these people bought the cameras. Maybe this guy bought 2 cameras, this guy bought 1, and indeed, first price auction has the property that it sets a price. Like you name the price, I gave you the item, so I know what the price was. Now I think of this as a game. It's a classical game theoretic game. Your strategy was the price. Actually, your strategy here was a price mixed with what you're bidding on. But I'm going to think of you bidding 0 on the things you're not bidding. So just your price. You have a price vector. This guy, for example, was bidding P1 and P3 on these 2. Okay, this auction set the price. Remember, the basic concept we wanted to think about is Nash equilibrium. So let's think of what the Nash equilibrium of this auction looks like. Now, I don't know if some people, especially of Kusha's class, might be worrying to tell me that this game will not have a Nash equilibrium. That's an excellent point. Stop worrying about that for a second. But let's suppose it has a Nash equilibrium. Okay, it may or may not have a Nash equilibrium. Stop worrying about that. Suppose it has one. Suppose this actually is the Nash equilibrium. This price is unwritten here with some other bits the other people did. Suppose that's a Nash equilibrium. Now, there's an interesting property of this Nash equilibrium. This person here, who I highlighted with yellow, in this Nash equilibrium, everyone currently doing what's best for them. So this guy can look at the best Nash equilibrium, look at the prices, and behave exactly how he would in the supermarket. In this stable outcome, these are the prices. If he doesn't like his outcome, and he probably won't because he couldn't get a damn thing in my solution, he could just bid a little bit above the current price and win whatever he wants. So effectively, his experience is precisely the supermarket experience. The Nash equilibrium set the prices, and he can go in the supermarket and buy the goods at the prices available. Well, okay, plus a little bit epsilon more. And then he wins whatever he wants to win at these prices. If this is a Nash equilibrium, apparently this isn't good for him. Otherwise, it wouldn't be a Nash equilibrium. So what's the inequality we get out of this equilibrium? First of all, we have a special bid here, namely bidding a little bit above the prices, that will have the property that if he bids this B prime I bid, his person I, and everyone else stays with his current bid, he can get whatever he wants, his favorite set of items, which I called SI star, his favorite package, at the current prices, summed up all the prices. This is the supermarket experience. He can go in and look at the prices and collect his favorite set of goods at the current prices. And he can do this. He has a bid to do this. So this means that if he is currently happy with this, then his current outcome is at least as good as this, and that in particular means that Nash equilibrium generates what's called market clearing prices. Everyone's happy, every good went home with someone, whoever bid the highest, and they cleared the market, and everyone's happy with this outcome. This is coming from a paper of Bicchandani in '96. What's nice about market clearing prices is that market clearing prices guarantee that the outcome is socially optimal. Okay, so step number one, I claimed that if this first price auction has a Nash equilibrium, some set of prices that are equilibrium, then those behave like the supermarket does. Everyone can do whatever they want. And because it's equilibrium, they don't want to do anything else what they're doing. So this current set of prices, everyone's happy, the market clearing prices. And then I'm going to claim that market clearing prices are socially optimal. And why are they socially optimal? Because everyone's utility is as good as they could have grabbed the optimal set of items. If I take that inequality, and this is what we're claiming, each player has value currently that's better than his favorite item, set of items, this is the inequality. His current set of items minus the prices is bigger than his optimal set of items minus what that would have cost. I sum this over the players, and notice that the prices fell out because they're both sides of the inequality. So the current value is bigger and equal than the optimal value I'm set. What's nice here, by the way, that absolutely no assumptions on the values. I promise you up front that I will make that you're all less hungry if you have more food already. This is not in here. I didn't have to assume anything. Market clearing prices are magic. What's wrong with them? They tend not to exist. That's what's wrong with them. But when they exist, they're magic. So what we got here, going back to the first slide, is that first price auction, if it has a Nash equilibrium, it's optimal, socially optimal, it's perfect. What's wrong with first price auction is tend not to have a Nash equilibrium. And what I would like to do is something like this, but I want it to be more robust. What does it mean more robust? Pure Nash equilibrium might not exist. Well, those of you who listened well, or again in Arkusha's class, remember that Nash equilibrium, of course, is guaranteed to exist. That's what Nash is famous for. But in the Nash equilibrium that is guaranteed to exist, you have to randomize. And if you randomize, I couldn't do this P plus, because your price is random. And a random P, I can't outbid you so easily. I outbid you with some probability, but I can't do exactly a step above you. In a real market, there might be other problems. I tried to tell you in the beginning that people this is a market that evolves, and people have to learn how to play it. It's not at Nash equilibrium. That's this point here. It's a repeated game in which people learn to play. They're not currently at some Nash equilibrium. It's not even clear what that might mean. People might not know who else is bidding. In the online advertisement, there are other factors that the advertisers are setting, or more precisely, Google is setting, like click-through rate and other quality factors and other numbers. They're not fully aware of the properties of the auction, so there's randomness around here. People might have probabilistic beliefs, or in fact, they should have probabilistic beliefs about the environment, both what Google is doing, which indeed Google is running a machine learning algorithm, so there are all kinds of factors that are hard to predict, and who else is participating. So this P plus, that you had to know exactly what the price is and outbid it a bit, that works in the supermarket. It doesn't work here, because we don't know what else is going on here. So what we would like to do is something like what what happened in that auction, but I want to do it more robustly. And the version of more robustness I like the most is this learning. So that was the point from here, that play is a repeated game in which people are learning to play. So let me spend 2 slides on that one before I tell you our results. So what does learning mean? So the concept of learning that I would like to use, and I want to emphasize of this as maybe the nicest concept or most important aspect, is it's a version where every time step we're running an auction, and every time step we're running maybe first price, second price, whatever you're running, people are bidding. And as a participant, you do something, and initially you're not really sure what you should do, but as time goes on, hopefully you learn. So in the beginning you don't know, later on you sort of learn what to do. I'm hoping that you can achieve this property. That is, over time, you might want to, on the mornings, bid high and the evenings, bid low. On Mondays, bid high, on Sundays, bid low. That might be the best thing you could do, and we might learn to do this. But at the bare minimum, if there is a single price that does very well consistently, please notice that one. Okay, so you could do more sophisticated things than this. You can change your bid depending on the time of day or other things. But I'm asking you that your total utility together, you should be at least as big as a single bid with hindsight. If there's a magical bid that's good with hindsight, I'm hoping you could get that one. As it turns out, this is not a hard standard. They're very simple natural algorithms that achieve it. I'm not suggesting you run my algorithm. I'm suggesting my existence of my algorithm, it's not mine, existence of many well-known algorithms for this, such as regret matching or weighted majority or multiplicative weight updates, that the existence of these algorithms should make you feel good about this belief. I'm not asking anyone to run it, but I'm handing it to them. Hey guys, you could do better than this, and if you do, congratulations. But if you do worse, here is an algorithm. You could do this one instead. So this is not a model of what people should do, not a prescription for them. It's a modeling behavior, modeling assumption. I'm assuming people are at least this smart, preferably smarter, but at least this smart. And I want to claim that whatever I claim about the outcome should be true under this assumption. Okay, I have to assume something about the rationality of the participant instead of assuming that they reach Nash equilibrium, assuming this. This is weaker than Nash equilibrium. If they are at Nash, then obviously they should have no regret. This is exactly the Nash assumption if I delete all the t's from here. Okay, if the outcome is stable, they're always doing the same thing. This is precisely the Nash assumption. But it's a weaker assumption than Nash. Okay, this apparently we had earlier for some reason which I don't understand. And there is a second aspect here of the uncertainty of the participant, which I'm actually deleting due to lack of time. And what we're hoping to do is take that market and pricing thing that you have seen on the first price auction and just lift it magically. And we have seen it doesn't lift, because I don't know how to beat P prime plus, but it almost does. It almost does, and this is what I want to show you. So here is what I want to do. This was the market clearing price, and with the picture here to remind you. So this is the magical price P plus, where people can just slightly outbid it. And what I want to do is change this a teeny bit and say, if you only had something magical you could do here that does not depend on what other people do. If I had a special bid that could do what I'm doing here, that does not depend on other people's behavior, I would be all set. This is precisely what the learning thing would like me to do. If I had a magical bid that does not depend on what everyone else was doing, that is unlike the price, because it doesn't depend on them, then I could ask you that, hey, you could do whatever you want, but I have a special bid for you. Why don't you do, you can do better, but if you're doing worse, here I have a proposal for you of what you could do. And that would exactly guarantee high outcome, high reward. So here is the general definition. It comes in two parts. First of all, I took the market clearing inequality and put in two fudge factors to make my life a little better. Remember, I used to do approximation algorithms before I got into this. So a little approximation is OK with me. So instead of requiring that you can grab your optimal good at the current prices, I'm instead requiring that you grab something quite as good as your optimal bundle with a lambda fudge factor. Think of lambda as a half. You can get half the value. And well, not quite at the current prices, but maybe twice of the current prices. Remember, I used to do approximation factors. These lambda and mu are approximation kind of things. And in fact, if you want, I don't have to require it for every person. I only can require it in aggregate. And then the theorem we had that this kind of mechanisms are optimal. Remember, first price was truly, really optimal. We're losing this lambda mu factor. You bought it twice the current price, you lost a factor of 2. You only got half your utility, you lost another factor of 2. So it depends what lambda and mu are. You're losing the product of them in utility because I put in the fetch vectors. I did this because I wanted to make my life easier. But then I want to make my life harder, because now I'm insisting that you should be able to do this not with a p plus, but with something that only depends on you, that you know you could do. Whereas p plus you cannot do because you don't know what p plus is. So the theorem is, which I was sort of leading up to, is that these kind of mechanisms are approximately optimal. They're losing a factor of mu over lambda, and they have all kinds of nice properties. They compose well in different mechanisms, and also true for learning outcomes, mixed equilibria, uncertainty about bidders. What the price is, you could bid that price a little bit up and win the item. And I claimed that with my fudge factors in there, I can do this without knowing the price. This still seems magical. And I'm going to convince you of this of first price auction. It works on every auction virtually on the universe, but I'm going to try it on first price auction. What I'm going to try is asking you to bid half your value. And now it's very important. Remember, I don't ask you to do this. I'm asking you to do at least as well as this. You're welcome to do whatever you want. If you do worse than this, that's pretty silly because I gave you a good advice. Okay, if I give you bad advice, you're welcome to do better. But you should at least do as well as this. And so what does it mean to do half your value? You bid half your value, you're at sort of a half approximation. The inequality was hoping for that in a single item auction, you're bidding half your value. Then what you should do is have this inequality true, that is get your true value minus the price. And I said it's a half-one approximation, so a half here and a 1 over there is the inequality I was hoping for. What can happen if you bid half your value in a first price auction? Well, you could win. You might regret that you won, that you priced too high when you won, but your net value minus the price is half your value. And remember, I believe in approximation algorithms, so this is a factor of 2 and we're okay. Well, sort of. Or you can lose. But if you lose, you're also okay, because if you lost, the price is above half your value. So this particular inequality, that you win something at least a fraction of your value at the current prices, that's actually giving you a negative lower band of what your utility should be, so obviously you satisfy that one. Okay, so if the price is above half the value, then this difference is negative and it says nothing, and so we're okay. My utility is a non-negative number, 0 in this case, and this is a negative number here. So this inequality is easy to reach, and in fact, half your value as a bid works in virtually every auction to achieve the same property. You can do better sometimes, and this wasn't optimized here. In fact, this works on virtually every sort of simple auction. First price auction, half wasn't a good idea, and you can do better. It can be 1 minus 1 over e, comma 1. Or pay auction, half your value works well. First price position auction, similarly. Second price, generalized second price. Even works on all kinds of other things, like a public project bidding where, or bandwidth allocation, or all kinds of other games that exist in literature that I won't elaborate on because I promised you that for this talk I stay with the individual item auctions. They all have the property that bidding half your value does the trick. It's an approximation. And sometimes not exactly half your bid, you can optimize the number better than half. What that means that bidding half your value works is that if I do simultaneous first price auctions on many, many items, that because of my composition theorem is now an approximation, now I have a good approximation guarantees. If I do simultaneous OPay auction that has good approximation guarantees, if I do a mix of simultaneous OPay first price, second price, that also is a good approximation. So the one thing I'm missing here is what is the assumption on composition. And I said it in English, but let me actually say it a little bit more technically, what I mean by this decreasing marginal utility. So I promised you that when you eat more, you're less hungry. That's basically the assumption. And to make it very concrete, what we want to assume is that winning something doesn't increase your value for something else. So the classical assumption here is if you are pairing a pair of shoes, the left shoe is utterly useless without the right shoe. So if it were the case that market 1 has your left shoe and market 2 has your right shoe, once you won market 1 on your left shoe, you suddenly your value for left shoe went way up. It was useless before and now it's useful. This is what I want to assume is not happening. So one way to model this is exactly the inequality that I originally claimed. If you have a subset S of items you have versus a subset of bigger set S prime, the value of an additional item X is greater if you originally have less. Okay? If you eat more, you're less hungry for the next food. This is the assumption. Under this assumption, and in fact, I only have to make this assumption across different markets. Within one market, I don't care. But things that are sold separately should have this property, that you want more on the other markets, you should be less interested in an item than if you want less on the other markets. So this is my general assumption across the different mechanisms, and under this assumption, if each of the individual components have this lambda mu approximation property, then the composed market also has the lambda mu approximation property, and due to the maybe lack of time, I actually will also skip the proof. So this is what I basically wanted to tell you as the basic story, and actually going back to the main message, maybe there are 3 bullets here that are worth separately elaborating. Remember the very beginning, there is tragedy of the commons. Selfish behavior can ruin social welfare. Okay? The story was that the unique selfish outcome is everyone grazes a lot of grass on the grass, and that's really bad for all of us. This can happen in routing, it can happen in markets, it can happen everywhere, or at least in many, many cases it can happen. But sometimes we can have mechanisms or setups that mediate the welfare loss. In the routing case, having enough capacity mediated the welfare loss. Here it seems like this very simplistic pricing can do it. This very simple first price, second price, OPE, all these pricing-based mechanisms are good at mediating the pricing loss. There are mechanisms that do badly, but basic message here is that price-based mechanisms do okay. They're not optimal, they're not perfect, but they do okay. Okay, in my theorems means a welfare loss of sometimes a factor of 2, sometimes 1 minus 1 over E. It's a theoretician's okay necessarily, and one can wonder in experimental setup of how okay is this really. But they certainly not do as horribly as the tragedy of the commons, which is an unbounded factor deterioration. And a further advantage that this sort of, when I say they do okay, I can say it does okay in an incredibly robust kind of way. That it's not only true in a single outcome and not only true under some stability assumption, but it's okay when there's uncertainty about what exactly the game is, like what Google is doing really. There's uncertainty about who else is participating, that's the uncertainty bullet. And okay if people are learning to play and they didn't reach an equilibrium, but they're sort of behaving rationally, and my assumption on this rationalness is that they maintain this no regret property, which to me seems a very natural property, and it's algorithmically definitely very achievable. So there is welfare loss, it's not perfect, but at least it's not much or it's limited, and it's very robust, and I'm going to stop. And thank you very much.
In terms of comparing the outcomes here to equilibrium, using the notion of price of anarchy, you're comparing it in a pessimistic way to the worse equilibrium. I don't know if in the settings that you were talking about, it's possible to have multiple equilibria, but isn't that too pessimistic? And if so, in other words, if there are multiple equilibria, isn't that too pessimistic a comparison, and wouldn't it actually be even better typically? Because, I mean, if you're comparing two equilibria, you might as well compare to the average equilibrium or the best equilibrium, so it's price of stability. So what is the right comparison there?
I guess there are sort of two embedded good questions in here that let me try to answer both or separate them a little bit. First of all, that these games tend to have multiple equilibria. And maybe a more optimistic analysis would say that there exists a good equilibrium, so let's analyze that one. That would be sort of the most optimistic analysis. So for example, on the generalized second price, which is what auctions get sold on, that's sort of the most famous paper is exactly of that vein. It has a good equilibrium, so let's analyze that one. In one sense, I'm kind of, I really like this last bullet, that this form of analysis is incredibly robust, and that it is valid not only on the multiple Nashes, but on learning outcomes and all kinds of other things. And this other format of analysis is not known to be, have this property. So I guess I'm not claiming this to be definitely the right number that I'm coming this way. It sort of might be too pessimistic, as Kusha says, and I'll come back to the second part of your question. But I object to analysis which somehow doesn't take this robustness into account, is not valid in this robust kind of way. We playing these games, or the whatever advertisers or companies are playing these games without knowing all the parameters. It's a well-known fact that nothing is stable in this game, so we're not reaching a Nash. So analyzing Nashes, whether they're unique or not, is a bit unfair here. And so I personally very interested in only robust findings, only findings that are valid under these assumptions also, with uncertainty in the background, with learning of behavior of participants. And so that's one part of the question. The second part of the question, are these findings are worst case and therefore pessimistic? And there you're totally right. This is a worst case, and worst case is when you decide that something is at most a factor of 30% of efficiency loss in a worst case, you can be very, very happy because this is worst case. In reality, it's going to be better than that. It's guaranteed. No matter what, it's this much efficiency loss at most. But you can also be unhappy that, especially when I said factor of 2, that's 50% efficiency loss. Hey, that's a lot. And what Kusha points out, that in reality, life might be better. And I would be very interested, and I am working on trying to show that life typically is better under some sort of average case analysis, or under actually better understanding what user behavior is really like. Here I'm not modeling user behavior, I'm modeling a very simplistic property of user behavior, and making stronger assumptions of how people behave or how the bidders behave. One could possibly get better results, and that would be really nice. So you're right, it's pessimistic. I guess I'm more interested in a more optimistic or more realistic or more predictive answer only if we kept the robustness and not via an equilibrium selection.
So I can't claim to understand everything, but I'm wondering how this might apply to the stock market, because you have effectively a repeated auction by people trying to buy shares of stocks, but sometimes it goes wrong. You get a bubble on a stock or something like that, and it doesn't seem like it's efficient there. And I know, stock market people always talk about this is an efficient mechanism for, pricing of commodities and things like that.
So one important aspect, and here the kind of theory I'm doing is not going to necessarily, I don't see how to make this better, is that I very much focused on long-run averages. That is what's typically often going wrong, or typically or frequently going wrong with the stock market, is these bubbles. And I'm in some way, in a theoretical way, I'm washing out the bubble by saying that when the time is long enough, on the long-run average, things work out okay. So in a way, I'm taking that problem go away. Now, it would be better to understand better, for example, the convergence properties of these methods. That is, how long a term do I have to take before my analysis starts being valid? And that depends on, so I made the assumption that people use algorithms that learn what the right bidding behavior is. And I guess I have to make assumptions now about how fast people are learning. That is how speedy the learning process really is. And presumably, though I guess I don't know any, certainly no theoretical analysis, if this average hits faster, if this theorems hit faster or learning hits faster, that limits the size of the bubbles. This will always allow some bubbles, because any analysis of this form, it only can talk about long-term averages, but will limit the size of the bubbles. It's a good question. There are other assumptions under here that might not be fully true on the stock market. Like I'm assuming that people have a particular value for the item. It's a reasonable assumption on advertisement. Advertisement is your eyeballs and your interest in buying their product, and then must have a private value to people. I'm further assuming they know this private value. This is probably a bad assumption. They tend not to know this private value. The stock market has both the uncertainty of the value, that people don't really know what the value is, what they're buying, and furthermore, it might not actually be fixed. There's some common value component of this that's not assumed here. It's better model of the advertisement market, where you as an advertiser have a private value for someone seeing your advertisement. The stock market is more a common value setup. So in some way, I'm not modeling it, but there are bubbles even in this one.
So I have a last question, which is, you've designed mechanisms to mitigate welfare loss. Can you go one step further and penalize selfish behavior?
Can I penalize selfish behavior? I'm sure I could. And in fact, once there are methods for offering people penalties, I could, in principle, do something that gets to the truly optimal solution. So on the trade-off, I was sticking to simple mechanism. I could do the following non-simple thing. I could do social optimization, figure out somehow the welfare, and then and what the optimal welfare is, and then tell you guys that that's the solution. Like, figure out which way you're supposed to drive to work, and tell you which to drive to work that way, because that's a socially optimal solution, and tell you that if I see you driving the other way, you go to prison or something. In in routing, it will be possible. It's not physically possible. That is in internet packet routing. Well, it wouldn't occur to someone to put into a giant linear program the optimization problem of how to route packets. They're just too big. In the internet setup or the auction setup, these values are really truly, how are you going to, sometimes you can't know what the true number is. In fact, all honesty, sometimes even the owners don't know what the number is. But I certainly don't know it outside, so I don't know how to penalize it. So it's a mix. Sometimes I cannot do it because the secret number that they may or may not admit selfishly is a number that I simply has no outside evidence of what it is. They know it themselves, so it's really secret to them. Or sometimes I could, and I'm actually more interested in the second argument, I could in principle do this, but it's incredibly complicated and heavy-handed. And what the beauty, I think, of these mechanisms, or even allowing packets to just go on shortest paths, which is sort of what we try, certainly what we're doing with our cars. And even the internet is a good approximation that we're trying to send our packets on what is individually the shortest path, is that the mechanism is very simple, and the welfare is pretty reasonable. And welfare optimization of the kind that punishes, it needs an awful lot of policing, as in you have to check what exactly is going on. And that sort of coordination itself has its own expense. It's not in the model right now, because the model just says the time and not the organization cost. But truly speaking, I guess one can say this in. So if I were to give a talk on the selfish routing kind of stuff, so anything that's systems organization, I would say that that analysis is step one in a two-step process. You should do this, and then think about it, whether the welfare loss is big enough to make it worse, putting in more control and more policing. In the internet version and pricing version, I guess I can't even say that because the values are, I can't penalize you for not admitting your value. You don't know it.
At the beginning of your talk, you emphasized the efficiency of the auction process. You said these things had to be done in 40 milliseconds and so on, but you didn't explicitly introduce that again in the talk, unless that was what you meant by simplicity. I wasn't sure.
Yeah, so it's an excellent point, and maybe I should have emphasized that unlike efficiency, which I mean welfare, social welfare maximization, or what I mean by truthfulness, which I wasn't using at all, I don't have a clear definition of what simplicity is, but you need to do something that can run in this millisecond framework, so something that can get implemented fast. Certainly, individual first price, individual second price, those are very simple. I don't, at the moment, have a clear enough definition of what else would be allowed in this framework, or what, the running, like that I want it to be sublinear running time, or what exactly I mean by simple.
But would something like saying it has to be a constant time calculation or linear time or something, would that be the kind of thing you have in mind?
What I mean is something has to be very, very fast to implement. Like the point is that it's going to run in this millisecond framework, so anything complicated is not okay.
Okay, well, I think it's time to give Eva a break, and I hope everyone will be able to join us. There'll be a reception just outside in the atrium, but before we go, let's thank Eva once again for a fabulous talk.
This production is brought to you by the University of Edinburgh.